Equilibrium involving dissolution of solids or gases in liquids. Solids in liquid. We know from our experience that we can dissolve only limited amount of salt or sugar in a given amount of water at room temperature. We make a thick sugar syrup solution by dissolving sugar at a higher temperature. Sugar crystals separate out if we cool the syrup to room temperature. We call it a saturated solution when no more of solute can be dissolved in it at a given temperature. The concentration of solute in a saturated solution depends upon the temperature. In saturated solution, a dynamic equilibrium exists between the solute molecules in the solid state and in the solution. Sugar solution in equilibrium with sugar solid, and the rate of dissolution of sugar is equal to rate of crystallization of sugar. Equality of two rates and dynamic nature of equilibrium has been confirmed with the help of radioactive sugar. If we drop some radioactive sugar into saturated solution of non-radioactive sugar, then after some time radioactivity is observed both in the solution and in the solid sugar. Initially there were no radioactive sugar molecules in the solution, but due to dynamic nature of equilibrium there is exchange between the radioactive and non-radioactive sugar molecules between the two phases. The ratio of radioactive to non-radioactive in the solution. The ratio of radioactive to non-radioactive molecules in the solution increases till it attains a constant value. Gases in liquids. When a soda water bottle is opened, some of the carbon dioxide dissolved in it fizzes out rapidly. The phenomenon arises due to the difference in solubility of carbon dioxide at different pressures. There is equilibrium between the molecules in the gas state and the molecules dissolved in the liquid under pressure. CO2 gas to CO2 in solution. This equilibrium is governed by Henry's law, which states that the mass of a gas dissolved in a given mass of a solvent at any temperature is proportional to the pressure of the gas above the solvent. This amount decreases with the increase of temperature. The soda water bottle is sealed under pressure of gas when its solubility in water is high. As soon as the bottle is opened, some of the dissolved carbon dioxide gas escapes to reach a new equilibrium condition required for the lower pressure, namely its partial pressure in the atmosphere. This is how the soda water in bottle when left open into the air for some time turns flat. It can be generalized that for solid to liquid equilibrium there is only one temperature melting point at 1 atmosphere 1.013 bar at which the two phases can coexist. If there is no exchange of heat with the surrounding, the mass of two phases remains constant. For liquid vapor equilibrium, the vapor pressure is constant at a given temperature. Dissolution of solids in liquid solubility is constant at a given temperature. For dissolution of gases in liquid, the concentration of gas in liquid is proportional to the pressure concentration of gas over the liquid. So these observations are summarized in this table. So liquid to vapor equilibrium, that is pressure constant at given temperature. Solid to liquid, melting point is fixed at constant pressure. Solid to solute solution. Concentration of solute in solution is constant at a given temperature. Then gas aqueous upon gas in the gas phase is constant at a given temperature. CO2 aqueous upon CO2 gas is constant at a given temperature. General characteristics of equilibrium involving physical processes. For the physical processes discussed above, the following characteristics are common to the system at equilibrium. Equilibrium is possible only in a closed system at a given temperature. Both the opposing processes occur at the same rate and there is a dynamic but stable condition. All major properties of the system remain constant. When equilibrium is attained for a physical process, it is characterized by constant value of one of its parameter at a given temperature. The magnitude of such quantities at any stage indicates the extent to which the physical process has proceeded before reaching equilibrium.